In this example problem, we have a car going around a vertical loop. So I'm going to start by drawing the track. There's the vertical loop. And the car, at the point we care about, is along the top of that loop. And we're given a radius of the loop, r. So I'm going to write down the things I know for all these problems. We have the mass of the car. Now in part B, they give you a value, but they don't give you a value in part A. So I'm going to solve part A without the mass for now. We know the radius of the circle, which is 20 centimeters, but we need to be careful because we always want everything in meters, kilograms, and seconds. So to convert that to meters, I want to get rid of centimeters and go to meters, and there's 100 centimeters in 1 meter. So I'm dividing by 100, and so I'm going to get 0.2 meters. The other thing I want to do is look at the forces acting on that car. So I'm going to draw a free body diagram. The free body diagram is going to have the car. That is not a good car. We'll try that again. It's wheels. It's upside down. And we always have FG pulling down. All right. There will be a normal force since we're on a track, and the normal force pushes perpendicular to the track. It's the track pushing on the car, so it actually also goes downward. And there's going to be some friction as well, which I don't think we're going to have enough information to find, nor do we really need it. What we really care about are the forces that act along the centripetal axis. And when we're going towards the center, we'll call that the positive direction. So again, in this picture, that's my positive direction for the centripetal axis. And I'm going to list those forces in my table. I have Fg. I'll write that in red just to be consistent. And I have the normal force. Fg, since we're on Earth, is going to be the acceleration due to gravity, 9.8, times the mass. F equals ma. And I'm going to write it as positive because the direction of that force is towards the center. The normal force is also a positive value. However, for part A, they tell you the minimum speed at which the car can go before it falls off the track. So we want to know that tipping point when the car leaves the track. And when the car leaves the track, the normal force becomes 0. 0 newtons when the car leaves the track at that minimum speed. And the other variable we typically deal with is our acceleration. It's a centripetal acceleration, and so we have v squared over r is our centripetal acceleration, and it's also positive because it's going towards the center of the circle. And so now, like all of our force problems, we have the sum of all the centripetal forces equals the mass times the centripetal acceleration. The centripetal forces are gravity and the normal force, and they equal the mass of the car times the velocity squared over the radius. And gravity is 9.8 times the mass. The normal force is 0, so that goes away. So that we set that equal to m v squared over the radius, which is given as 0.2. And if you notice, a lot of these problems, the mass is on both sides of the equation in all terms, so the mass cancels. I can multiply both sides by 0.2. So I have 9.8 times 0.2. I'm trying to isolate the velocity. I get 1.96 equals v squared, which I then take the square root, and I get a velocity when the car just falls off the track of the square root of that answer, which is 1.4 meters per second. That's my answer for part A. Now, in part B, they give us another scenario. The car is actually going faster. And since it's going faster, it will feel a normal force on the track, and they want to know what is that normal force. So for part B, I'm now given a mass, and it's 20 grams. But again, I always want MKS, meter kilogram seconds, so I'm going to cancel grams and go to kilograms. And there's 1,000 grams in a kilogram, so I'm going to get 0.02 kilograms as the mass of the car. The acceleration of the car is a centripetal acceleration, which is the velocity squared over the radius. And they tell us the new velocity is 1.8 meters per second, and we know the radius is still 20 centimeters, 0.2 meters. So I can plug in 1.8 squared over the radius, 0.2. 1.8 squared divided by 0.2, and I get a centripetal acceleration of 16.2. And I still have the same forces. I have Fg, which is 9.8 times the mass, which is going to be 9.8 times 0.02, which is 0.0196 newtons. And again, that's towards the center. And the normal force is what I'm trying to find. That's some things that disappeared on me. The mass is 20 grams. And so now, again, I'm setting up F equals ma. The sum of all the centripetal forces equals the mass times the centripetal acceleration. Those forces are Fg plus the normal force. They both act towards the center, so they're both positive, and that's mass times the centripetal acceleration. And now I'm going to plug in the values I know. Gravity is 0.0196 plus the normal force, and that's equal to the mass, which is 0.02 kilograms, times the centripetal acceleration, which we calculated as 16.2. 16.2 times the mass, it gets me my net force of 0.324. On the left side, I still have gravity, 0.196 plus the normal force. And now I'm going to subtract gravity from both sides. And I believe I have an extra zero in there. I believe it should be 0.196 here. I'll adjust that here. Found my typo. Looked a little bit small. And when I subtract 0.196, the force of gravity from it, I get my normal force of 0.128. Fn equals 0.128 newtons. There you have it.